The Pacific Ocean stretches endlessly beneath the research vessel's hull. Waves roll in perfect rhythm, each one carrying the memory of storms born 1,000 miles away. Dr. Sarah Chen stands at the bow, her instruments detecting something impossible. The magnetic readings don't match the charts. The gravitational measurements defy explanation. Deep beneath these waters, something massive has shifted, and the very axis of our planet bears the scars of an ancient catastrophe that science is only beginning to understand. For decades, we've accepted the comfortable notion that Earth spins on a stable axis, wobbling gently through space like a well-balanced top. Our textbooks speak of gradual changes, slow drift, the patient accumulation of ice that might nudge our planet's rotation by fractions of degrees over millennia. But what if that story is incomplete? What if the forces that shaped our world were far more violent, far more sudden than we've dared to imagine? Across the globe, evidence whispers of a different tale. In Siberia, mammoth carcasses lie frozen in poses of sudden terror, their stomachs still full of tropical vegetation. In the Sahara, whale bones rest beneath sand dunes where no ocean has flowed for thousands of years. Along coastlines from Japan to Chile, ancient coral reefs sit stranded hundreds of feet above modern sea level, as if the ocean itself had abandoned them overnight. These are not the signatures of gradual change, they are the footprints of catastrophe. The mathematics of planetary motion reveal uncomfortable truths. Earth's axis has wandered throughout history, sometimes by degrees that would reshape continents and relocate the very poles themselves. But conventional geology insists these movements happen slowly, imperceptibly, across millions of years. The evidence suggests otherwise. Deep ice cores from Greenland show temperature swings of 40 degrees Fahrenheit within single decades. Sediment layers speak of floods that dwarfed anything in recorded history. Magnetic reversals appear in rock strata with a suddenness that defies explanation. What could cause such dramatic shifts? The answer may lie not in the gradual accumulation of ice or the slow dance of tectonic plates, but in something far more spectacular. Giant floods, deluges so vast they could literally tip the planet, redistributing mass with such violence that Earth itself would stagger like a spinning coin struck by an invisible hand. Consider the physics involved. Our planet spins because of its angular momentum, a delicate balance between mass and motion that has remained relatively stable for billions of years. But that stability depends on how weight is distributed across the surface. Move enough mass from one region to another quickly enough, and the entire system can shift. It's the same principle that causes a washing machine to shake violently when clothes bunch up on one side during the spin cycle. Only imagine that washing machine is a planet, and the unbalanced load is billions of tons of water moving faster than any flood in human memory. The geological record preserves hints of such events. In Washington state, the channeled scablands stretch across thousands of square miles, carved by waters that moved with unimaginable fury. Geologist J. Harlan Bretz first proposed in the 1920s that these landscapes were shaped by catastrophic floods, not gradual erosion. His colleagues dismissed the idea as heretical. Geology, they insisted, was a science of slow processes, not sudden disasters. But the evidence wouldn't disappear. Massive boulders scattered like pebbles, canyon systems carved in hours instead of millennia, ripple marks the size of city blocks. Eventually, science accepted what the rocks were saying. The Missoula floods had indeed reshaped an entire region in a matter of days. But the channeled scablands represent just one flood in one region. What if similar deluges occurred simultaneously across multiple continents? What if the melting of Ice Age glaciers didn't happen gradually over thousands of years, but suddenly, catastrophically, in bursts that sent incomprehensible volumes of water racing across the landscape? Recent climate research suggests this scenario is not just possible, but probable. Ice sheets don't melt uniformly, they collapse. When temperatures rise beyond critical thresholds, massive ice dams fail simultaneously, releasing lakes the size of entire countries in explosive bursts. The Laurentide ice sheet that once covered much of North America contained enough frozen water to raise global sea levels by 400 feet. If even a fraction of that mass had been released suddenly, the resulting floods would have made biblical deluges look like spring rain. Imagine walls of water a mile high racing across continents at hundreds of miles per hour. The sheer momentum would be staggering. As these floodwaters carved new channels and deposited sediments thousands of miles from their origins, they would redistribute mass on a scale sufficient to affect planetary rotation. The North Pole, which currently sits in the Arctic Ocean, might have wandered hundreds or even thousands of miles from its previous position. Entire climate zones would have shifted overnight. Tropical regions could have found themselves at Arctic latitudes, while polar landscapes suddenly basked in temperate warmth. The evidence for such dramatic relocations appears in the most unexpected places. Coal deposits rich in tropical plant fossils lie beneath Antarctic ice. Palm fronds and fern impressions mark regions that now experience perpetual winter. These discoveries have traditionally been explained through continental drift, the slow movement of land masses over hundreds of millions of years. But what if some of these climate shifts happened far more recently within the span of human memory? Ancient maps seem to preserve fragments of such memories. The Piri Reis map of 1513 shows Antarctica's coastline with startling accuracy, centuries before the continent was officially discovered and millennia before modern technology could peer beneath its ice sheet. The Orontius Phineus map of 1531 depicts the same landmass free of ice, marked with rivers and mountains that match the hidden topography revealed by ground-penetrating radar. How could medieval cartographers have possessed such knowledge unless they were copying from far older sources? Maps drawn when Antarctica was indeed ice-free and habitable. The implications are staggering. If Earth's axis shifted suddenly and dramatically within human history, entire civilizations might have been caught in the transition. Advanced cultures that had developed around stable coastlines and predictable climates would have faced annihilation as their worlds literally turned upside down. The survivors would have carried fragments of their knowledge to new lands, seeding myths of great floods and lost golden ages that appear in every corner of the globe. These stories speak remarkably consistent language, from Mesopotamian tablets describing Utnapishtim's ark to Hindu texts recounting Manu's survival of the cosmic deluge, from Native American legends of the world being born from floods to Aboriginal Dreamtime stories of the great waters that reshaped the land. Each culture, isolated by geography and time, preserved memories of the same cataclysmic event. Water rising beyond imagination, the earth itself shifting, survivors clinging to whatever refuge they could find as their familiar world drowned beneath waves that seemed to touch the sky. Modern seismology adds weight to these ancient testimonies. The Earth's surface bears scars that speak of forces far beyond ordinary earthquakes or volcanic eruptions. Massive parallel ridges run for hundreds of miles across ocean floors, as if the planetary crust had been stretched and torn by unimaginable stress. Deep fault systems show evidence of simultaneous activation across multiple continents, suggesting that whatever force reshaped the surface operated on a global scale. Even more intriguing are the magnetic anomalies that pepper our planet's surface. Compass readings deviate from expected values in ways that suggest the magnetic field itself has been disrupted repeatedly throughout history. Some of these anomalies align with the boundaries of ancient flood deposits, as if the moving water carried magnetic materials that still influence navigation centuries later. Ships' logs from the age of exploration record compass variations that don't match current magnetic models, hinting that the field was still settling from some earlier disruption. The biological evidence proves equally compelling. Species distributions that make no sense under conventional migration theories suddenly become logical if continents experienced rapid climate shifts. Why do identical plant species appear on opposite sides of oceans with no apparent means of crossing vast water barriers? Why do deep-sea creatures that require specific temperature ranges show up in environments that should be hostile to their survival? The answer may be that these organisms didn't migrate at all. Their environments moved around them as the planet's axis relocated their habitats to entirely different latitudes. Paleontologists have long puzzled over extinction events that seem to coincide with evidence of massive flooding. The end of the last ice age marked the disappearance of megafauna across multiple continents. Mammoths, giant ground sloths, cave bears, and dozens of other species vanished within a geological instant around 12,000 years ago. Traditional explanations point to hunting pressure from expanding human populations or gradual climate change as ice sheets retreated. But the timing is too precise, too synchronized across regions that had no contact with each other. Something global happened, something that could eliminate established ecosystems simultaneously across vast distances. The answer may lie in the mechanics of axial displacement itself. When Earth's rotational axis shifts suddenly, the effects cascade through every system on the planet. Atmospheric circulation patterns collapse and reorganize. Ocean currents reverse or disappear entirely. Weather systems that had remained stable for millennia break down in a matter of years or decades. For species adapted to specific environmental conditions, such rapid changes would be utterly catastrophic. Those that survived would be the ones capable of extreme adaptability or fortunate enough to find themselves in regions where the new climate happened to suit their needs. Human populations would have faced the same challenges on an unimaginable scale. Archaeological evidence suggests that many advanced cultures disappeared abruptly around the same time period. The Clovis people of North America, whose sophisticated tool technology had spread across the continent, vanished almost overnight. In Europe, the Magdalenian culture that had created the stunning cave art of Lascaux and Altamira likewise disappeared from the record. Similar patterns appear in Asia, Australia, and South America. Not gradual decline, but sudden cessation, as if entire ways of life had been swept away by forces beyond human comprehension. The survivors of such cataclysms would have carried more than just genetic heritage forward. They would have preserved technological knowledge, astronomical observations, and cultural memories of the world that existed before the Great Turning. These fragments would have formed the foundation for new civilizations that arose in the changed landscape, explaining why so many ancient cultures seem to possess knowledge that appears advanced for their supposed level of development. Consider the precision with which early civilizations tracked celestial movements. The builders of Stonehenge aligned their monument to astronomical events with mathematical accuracy that rivals modern observatories. Mayan calendars calculated planetary cycles extending thousands of years into the future and past. Egyptian pyramids encoded relationships between Earth's dimensions and cosmic constants that weren't officially discovered until the space age. How did cultures that supposedly invented writing only recently possess such sophisticated understanding of planetary mechanics? The answer may be inheritance rather than innovation. If earlier civilizations had developed advanced astronomical knowledge through centuries of careful observation, that information could have been preserved through the catastrophic period and passed down to rebuilding cultures. The precision would reflect not primitive genius, but the accumulated wisdom of observers who had tracked the heavens through multiple axial shifts, recording the patterns of change that revealed deeper truths about planetary motion. This perspective transforms our understanding of human development from a story of gradual progress to one of recovery and rediscovery. We are not the first civilization to achieve technological sophistication. We may not even be the second or third. Instead, we represent the latest attempt by human intelligence to rebuild what was lost when the world last turned upside down, carrying forward whatever fragments of ancient knowledge managed to survive the great forgetting that accompanies such planetary upheavals. The evidence grows more compelling when we examine the quantum mechanics of planetary rotation itself. Earth doesn't spin in isolation. It wobbles, precesses, and oscillates in response to gravitational influences from the moon, sun, and distant planets. These forces create what physicists call resonance patterns, natural frequencies at which our planet responds to external stimuli. Under normal conditions, these resonances produce gradual changes measured in arcseconds per century, but introduce a massive disturbance at precisely the right frequency, and the response can be catastrophic. Think of an opera singer shattering a wine glass with her voice. The glass doesn't break because the sound is loud, but because the frequency matches the glass's natural resonance. Similarly, a flood of sufficient magnitude striking Earth at its resonant frequency could trigger oscillations that amplify far beyond the initial disturbance. The planet would ring like a struck bell, and that ringing could shift the axis by degrees rather than arc seconds. Computer models of such events reveal disturbing possibilities. When researchers at the Institute for Advanced Physics simulated the effects of multiple ice dam failures occurring within decades of each other, they discovered threshold effects. Below a certain level of water displacement, the planet's rotation remains stable. Above that threshold, the system enters what mathematicians call chaotic behavior. Small additional inputs produce enormous outputs. A flood that might normally cause regional devastation instead triggers global axial displacement. The timing of these threshold events appears to follow patterns that align with astronomical cycles. Every 12,000 years, Earth's orbit brings our planet closest to the galactic center during winter solstice, maximizing gravitational stress on the ice sheets. Solar radiation peaks coincide with these orbital extremes, creating perfect conditions for massive ice failures. The last such alignment occurred precisely when geological evidence suggests the most recent axial shift took place. Ancient astronomical texts seem to preserve awareness of these cycles. The Mayan long count calendar, which measures time in units of 5,125 years, may represent half of the 12,000-year cycle that governs axial instability. Hindu cosmology describes similar periods, calling them the breath of Brahma, during which the world dissolves and reforms. Even the biblical concept of Jubilee years, when debts are forgiven and society resets, may echo cultural memories of periodic global renewals, triggered by planetary axis shifts. The psychological impact of such events would have been as profound as the physical devastation. Imagine watching the sun rise in the west after a lifetime of eastern dawns. Picture the North Star suddenly appearing in an unfamiliar part of the sky, while constellations that had guided navigation for generations vanished below the horizon. The very foundations of reality would have seemed to crumble, leaving survivors to question everything they thought they knew about the natural world. This cognitive disruption explains why flood myths universally describe not just rising waters, but the breakdown of cosmic order itself. In Mesopotamian accounts, the deluge comes when the gods decide to unmake creation. Norse mythology tells of Ragnarok, when the world tree shakes and the old order collapses into chaos. Hindu texts describe the dissolution of reality during cosmic floods that wash away entire cycles of existence. These stories preserve more than meteorological memories. They record the psychological trauma of witnessing natural laws themselves appear to break down. The survivors who emerged from such chaos would have faced landscapes transformed beyond recognition. Familiar coastlines lay hundreds of miles inland or beneath new seas. Mountain ranges stood where plains had stretched to the horizon. Rivers flowed backward or had vanished entirely, leaving only dry channels as monuments to their former courses. The The very climate had shifted, turning deserts into forests and ice fields into temperate meadows. Archaeological evidence of these transformations appears in the strangest places. Beneath the Sahara Desert, ground-penetrating radar reveals ancient river systems that once supported vast civilizations. Lake beds the size of European countries lie buried under sand dunes, their sediments rich with the remains of tropical vegetation and diverse wildlife. Carbon dating places the end of this verdant period around 11,000 years ago, precisely when other evidence suggests major axial displacement occurred. Similar discoveries emerge from every continent. In Antarctica, ice cores reveal pollen from temperate forests that existed there within the span of human civilization. The Amazon rainforest shows signs of having been an arid grassland until relatively recently in geological terms. Australia's Great Barrier Reef sits in waters that were once dry land, its coral formations built on foundations of terrestrial rock. Each discovery adds weight to the hypothesis that Earth's climate zones have shifted dramatically and recently. The implications extend beyond archaeology into modern climate science. Current models of global warming assume that polar ice will melt gradually, raising sea levels by predictable amounts over centuries. But if ice sheets can collapse catastrophically, as the geological record suggests, then our projections may be wildly optimistic. The Greenland ice cap contains enough frozen water to raise global sea levels by 23 feet. The West Antarctic ice sheet holds another 12 feet worth of potential rise. If historical patterns hold, these masses won't melt slowly. They'll fail suddenly, simultaneously, creating floods that dwarf anything in recorded history. Modern satellite monitoring reveals disturbing signs that such failures may already be beginning. Ice streams in Antarctica are accelerating their flow toward the ocean at unprecedented rates. Massive ice shelves the size of small countries have collapsed within single summer seasons. Glacial lakes dammed by ice barriers are growing larger and more unstable each year. The same conditions that triggered catastrophic floods in the past are rebuilding in the present. The question is not whether another major flood event will occur, but when and whether human civilization can survive the axial displacement that would likely accompany it. Our modern world, built on the assumption of stable geography and predictable climate, would be even more vulnerable than ancient civilizations to sudden planetary changes. Coastal cities housing hundreds of millions of people sit at elevations that would be uninhabitable if sea levels rose suddenly by even 50 feet. Global supply chains depend on transportation networks that assume continents will remain in their current positions relative to climate zones. Perhaps most critically, our technological infrastructure relies on precise knowledge of Earth's magnetic field for navigation, communication, and power distribution. GPS satellites, electrical grids, and internet cables all function because we can predict how magnetic forces behave across the planet's surface. A sudden axial shift would scramble these systems, leaving modern society as lost and disconnected as ancient mariners whose compass needles suddenly pointed in impossible directions. Yet within this vulnerability lies opportunity. Unlike our ancestors, we possess the tools to monitor planetary systems in real time. Seismic networks can detect the earliest signs of ice sheet instability. Satellite imagery can track the movement of water masses before they reach critical thresholds. Computer models can simulate the effects of various displacement scenarios, helping us understand which regions might remain habitable and which would face extinction. More importantly, we can preserve knowledge in ways that transcend any single catastrophic event. Digital archives, genetic databases, and technological blueprints can be distributed across multiple continents and storage mediums, ensuring that future civilizations won't have to rediscover fundamental principles of science and engineering. We can build seed vaults, knowledge repositories, and communication systems designed to function even if the planet's axis shifts dramatically. The ancient builders who constructed monuments aligned to vanished star patterns may have understood this imperative better than we realize. Their stone circles, pyramid complexes, and megalithic temples weren't just ceremonial structures. They were information storage systems, encoding astronomical data, mathematical constants, and technological principles in forms designed to survive any conceivable disaster. The precision of their alignments reflects not primitive superstition, but sophisticated understanding of how to preserve critical knowledge across cycles of destruction and renewal. We stand now at a similar crossroads, possessing capabilities that exceed those of any previous civilization, yet facing the same fundamental challenge that has confronted every advanced culture in Earth's history. How do we prepare for the possibility that our familiar world might literally turn upside down? How do we ensure that human knowledge and achievement survive even if the ground beneath our feet shifts to entirely different latitudes? The geological clock continues ticking toward the next threshold event. Ice accumulates in polar regions while gravitational forces align in patterns that history suggests will trigger massive instability. The question that remains is whether we will recognize the warning signs in time to prepare, or whether future archaeologists will puzzle over the sudden disappearance of our civilization, just as we now wonder about the mysterious gaps in the human story that mark previous axial shifts. The answer may already be revealing itself in patterns we've only begun to recognize. Deep beneath the Pacific Ocean, research vessels equipped with the most sophisticated sensing equipment ever deployed are mapping gravitational anomalies that suggest our planet's mass distribution is far from stable. These measurements, precise to within billionths of a degree, reveal fluctuations that shouldn't exist according to conventional models of planetary mechanics. The Earth beneath our feet is not the solid, unchanging foundation we imagine, but a dynamic system constantly adjusting to forces we barely comprehend. Dr. Martinez adjusts the sonar array as another ping returns from the abyssal depths. The data streaming across her monitors shows something unprecedented: massive underwater mountain ranges that appeared on no previous charts, their peaks rising thousands of feet from ocean floors that were mapped just decades ago. These aren't gradual formations built over millions of years by volcanic activity. The sediment patterns, the magnetic signatures, even the way marine life has colonized these structures all point to recent emergence, geological yesterday in terms of planetary timescales. Similar discoveries emerge from research stations scattered across the globe. In Greenland, ice core samples reveal layers that tell impossible stories. Pollen from tropical plants embedded in ice that formed during what should have been the depths of Arctic winter. Marine microorganisms frozen into glaciers hundreds of miles from the nearest ocean. Volcanic ash from eruptions that occurred on the opposite side of the planet, carried by atmospheric currents that current weather models insist could never exist. Each anomaly alone might be dismissed as measurement error or contamination. Together, they paint a picture of a world in constant flux, where the familiar boundaries between climate zones, ocean basins, and even continents themselves are far more fluid than we've dared to acknowledge. The question becomes not whether dramatic shifts occur, but how frequently and what triggers them to cascade from local disturbances into global reorganizations. The mathematics of fluid dynamics offer clues that are both elegant and terrifying. When water moves in sufficient volume and velocity, it doesn't simply flow from high ground to low. It creates pressure waves that propagate through the Earth's crust itself, compressing and decompressing rock layers in rhythmic pulses that can destabilize fault systems thousands of miles away. These pressure waves travel at the speed of sound through solid matter, meaning that a catastrophic dam failure in one region can trigger seismic events on the opposite side of the planet within hours. But the most disturbing calculations involve angular momentum transfer. When massive amounts of water suddenly change direction, as they would during continental-scale flood events, they don't just carve new channels through the landscape. They transfer their rotational energy to the planet itself. Picture a figure skater spinning with arms extended, then suddenly pulling them close to her body. The change in mass distribution causes her rotation to accelerate dramatically. Now imagine the reverse process on a planetary scale, with water masses equivalent to entire oceans suddenly redistributing themselves across continents. The energy involved in such transfers defies comprehension. A single flood event carrying the volume of water that geological evidence suggests carved the channeled scablands would possess kinetic energy equivalent to thousands of nuclear weapons. Multiply that by simultaneous events across multiple continents, and the total energy release approaches the threshold needed to literally knock Earth off its rotational axis. Recent advances in satellite gravimetry have revealed that such redistribution events are not confined to ancient history. The 2004 Indian Ocean earthquake, which triggered tsunamis that killed over 200,000 people, also shifted Earth's axis by nearly 3 inches. The 2011 earthquake and tsunami in Japan moved it another 4 inches. These displacements, while small compared to the massive shifts suggested by geological evidence, demonstrate that our planet's rotational stability is far more fragile than previously understood. What makes these modern examples particularly significant is that they resulted from relatively minor crustal movements. The fault ruptures that caused these earthquakes displaced rock masses measured in cubic kilometers. The floods that ancient evidence suggests reshaped entire continents would have involved water masses measured in cubic thousands of kilometers. The axial displacement from such events wouldn't be measured in inches, but in degrees. Atmospheric physicists studying these phenomena have identified what they call resonance amplification effects. Just as a small push applied at the right moment can cause a playground swing to arc higher and higher, flood-induced pressure waves that occur at Earth's natural oscillation frequency can build upon each other, creating displacements far larger than the initial disturbance would suggest. Computer models of these resonance effects reveal threshold points beyond which small additional inputs produce catastrophic outputs. The geological record preserves evidence of such threshold events with startling regularity. Every 12,000 to 13,000 years, sediment layers show simultaneous disruption across multiple continents. Ocean floor cores reveal sudden changes in current patterns, as if entire circulation systems had reversed overnight. Ice core data from both poles show synchronized climate shifts that traditional meteorology cannot explain. The timing of these events corresponds precisely with astronomical cycles that maximize gravitational stress on Earth's ice sheets and ocean systems. Modern climate monitoring reveals that we are approaching another such alignment. Solar radiation cycles are nearing their peak intensity, while Earth's orbit carries us through gravitational fields that haven't been this strong in over 12,000 years. Polar ice sheets show signs of instability that mirror patterns preserved in geological strata from previous threshold events. The stage is being set for conditions that history suggests inevitably lead to catastrophic flood events and their associated axial displacements. The warning signs are subtle but unmistakable to those who know how to read them. Magnetic field fluctuations that cause migratory animals to lose their way. Gravitational anomalies that affect satellite orbits in ways that require constant correction. Seismic activity patterns that cluster around ancient flood boundaries. Deep ocean temperature measurements that show currents beginning to slow or reverse their traditional flows. Each indicator alone might be explained by natural variation. Together, they suggest a planetary system approaching critical instability. Indigenous cultures around the world preserve oral traditions that describe the warning signs their ancestors learned to recognize before the great waters came. Birds flying in wrong directions, fish appearing in unexpected waters, the aurora dancing in skies where it had never been seen before, springs going dry while new ones appeared in impossible places. These stories, dismissed by modern science as folklore, may preserve observational knowledge accumulated over thousands of years of surviving cyclical catastrophes. The Inuit elders of northern Canada speak of times when the sun failed to set for days longer than the seasonal cycle should allow, followed by winters that arrived without warning in the middle of summer. Aboriginal Australians describe periods when familiar constellations vanished from the sky while new star patterns appeared in their place. Polynesian navigators preserve chants that describe islands appearing and disappearing, forcing their ancestors to develop new navigation techniques based on ocean currents instead of fixed celestial references. These accounts share common elements that suggest they describe the same type of planetary scale disruption from different perspectives. The breakdown of familiar patterns, the sudden appearance of new geographical features, the need to develop entirely new ways of understanding the natural world. Most significantly, they all describe these changes as occurring within human lifespans, not across geological ages. Archaeological evidence supports the testimony of oral tradition. Settlement patterns show abrupt abandonment of coastal areas around the world, approximately every 12,000 to 13,000 years. Advanced civilizations that had flourished for centuries simply vanished from the record, their cities buried under sediment layers that could only have been deposited by massive flood events. The survivors appear to have migrated inland and upward, establishing new communities on higher ground with technologies and knowledge that seem anachronistically sophisticated for their supposed level of development. The precision of astronomical alignments in ancient monuments suggests that these survivor communities possessed detailed knowledge of celestial mechanics that could only have been acquired through centuries of careful observation. Yet the monuments themselves are often the earliest structures in their regions, built by cultures that had supposedly just emerged from primitive hunting and gathering. The contradiction resolves if we understand these builders not as innovators, but as refugees carrying forward the accumulated wisdom of civilizations destroyed by the previous axial displacement event. Modern engineering analysis of these ancient structures reveals construction techniques that remain challenging to replicate even with contemporary technology. Stone blocks weighing hundreds of tons lifted to precise positions and fitted together with tolerances measured in fractions of inches. Acoustic properties that suggest understanding of resonance and vibration that wasn't formally recognized by science until the 20th century. Mathematical relationships encoded in architectural proportions that demonstrate knowledge of planetary dimensions and cosmic constants. The builders of these monuments weren't primitive people struggling to understand their world. They were the inheritors of sophisticated scientific traditions that had developed methods for preserving critical knowledge across catastrophic disruption cycles. The stone circles, pyramid complexes, and megalithic temples scattered across every continent represent a distributed backup system, encoding essential information about astronomy, mathematics, and engineering in forms designed to survive any conceivable disaster. This perspective transforms our understanding of human cultural development from a story of steady progress to one of cyclical recovery. We are not the first civilization to achieve technological sophistication. We represent the latest iteration in a recurring pattern of rise, catastrophe, and renewal that has characterized human development for tens of thousands of years. Each cycle builds upon fragments preserved from the previous one, gradually recovering lost knowledge while developing new innovations suited to change planetary conditions. The implications for our current situation are profound. If the geological and astronomical evidence is correct, we are approaching another threshold event that could trigger massive floods and associated axial displacement. Unlike our ancestors, we possess global communication networks, satellite monitoring systems, and computational models that could provide advance warning of developing instability. We also have the technological capability to preserve vast amounts of information in forms that could survive even planetary-scale disruption. But we also face vulnerabilities that previous civilizations never encountered. Our population is concentrated in coastal cities that would be uninhabitable if sea levels rose suddenly. Our technological infrastructure depends on precise knowledge of magnetic field orientations that would be scrambled by axial displacement. Our food production systems rely on stable climate zones and predictable seasonal patterns that would be completely disrupted by sudden geographical shifts. The challenge before us is to prepare for possibilities that extend far beyond the gradual climate change scenarios that currently dominate scientific and political discourse. We need to develop systems that can function even if fundamental assumptions about planetary stability prove incorrect. This means creating distributed networks of knowledge preservation, establishing communities in geologically stable inland regions, and developing technologies that don't depend on precise satellite navigation or stable magnetic field orientations. More fundamentally, we need to expand our conception of natural disaster preparedness to include events that could literally turn our world upside down. The ancient monument builders understood this imperative, creating structures designed to preserve essential knowledge across any conceivable catastrophe. Their stone archives still speak to us across thousands of years, testimony to human ingenuity in the face of planetary-scale uncertainty. The next phase of this investigation requires us to examine the specific mechanisms by which massive flood events could trigger axial displacement, and to identify the early warning signs that such an event may be approaching. The data streaming in from research stations around the globe suggests that we may have less time than we imagine to prepare for possibilities that could reshape civilization itself. The morning sun casts long shadows across the research facility in northern Alaska, where Dr. Elena Vasquez adjusts the seismic monitoring equipment for the third time this week. The readings keep changing, not gradually as equipment drift would suggest, but in sudden jumps that indicate something fundamental is shifting beneath the frozen ground. Her instruments detect microfractures propagating through permafrost layers at unprecedented rates, creating networks of instability that extend far deeper than seasonal thaw patterns could explain. These aren't isolated measurements. Similar anomalies emerge from monitoring stations across the Arctic Circle, each one recording pressure changes that suggest massive underground movement. The permafrost, which has remained stable for thousands of years, appears to be entering a state of accelerated destabilization. But the implications extend far beyond local ground instability. Locked within these frozen layers are methane deposits and organic materials that represent millions of years of accumulated biomass. When permafrost fails catastrophically, it doesn't simply thaw, it explodes. The physics of methane hydrate decomposition reveal mechanisms that could amplify flood-induced axial displacement by orders of magnitude. These crystalline structures, formed under extreme pressure and low temperature, contain concentrated methane in ratios that dwarf conventional natural gas deposits. When the pressure drops suddenly, as it would during massive ground shifts caused by floodloading, the hydrates don't decompose gradually. They undergo explosive phase transitions, releasing enormous volumes of gas in geological instants. The energy released from such events defies easy comprehension. A single cubic meter of methane hydrate contains approximately 160 cubic meters of methane gas under standard conditions. Multiply this by the trillions of cubic meters of hydrates locked in Arctic permafrost, and the potential energy release approaches levels that could literally launch sections of the Earth's crust into temporary orbital trajectories before they crash back down, redistributing mass on scales sufficient to alter planetary rotation. Recent sonar mapping of the Arctic ocean floor reveals features that suggest such explosive decomposition events have occurred repeatedly throughout geological history. Massive circular depressions, some hundreds of kilometers in diameter, mark locations where the seafloor appears to have been blown upward and then collapsed back down. The rim structures around these formations contain compressed sediment layers that could only have been created by shock waves propagating through solid rock. Similar formations appear on land surfaces across Siberia, northern Canada, and Alaska. Local populations have long known these features as pingos or frost mounds, attributing their formation to gradual ice accumulation and seasonal freeze-thaw cycles. But detailed geological analysis reveals compression patterns inconsistent with slow formation processes. The structures show evidence of rapid uplift followed by equally rapid collapse, creating characteristic crater-like depressions surrounded by debris fields that extend for miles in all directions. The timing of these explosive events correlates precisely with the cyclical flood episodes preserved in global sediment records. Every 12,000 to 13,000 years, when astronomical alignments create maximum stress on polar ice sheets, the subsequent massive water releases trigger not only surface flooding but also pressure waves that propagate deep into the Earth's crust. These waves destabilize methane hydrate deposits, creating secondary explosions that can dwarf the energy of the original flood events. Computer simulations of such coupled flood explosion scenarios reveal cascade effects that traditional geological models never considered. The initial flood redistributes surface mass, creating gravitational anomalies that affect deep crustal stability. Pressure waves from the moving water destabilize underground gas deposits, triggering explosions that further redistribute mass and generate new pressure waves. These secondary waves can destabilize additional hydrate deposits, creating a chain reaction that propagates across entire continents. The mathematical analysis of these cascade effects reveals why axial displacement events appear to occur so suddenly in the geological record. The system remains stable until it crosses a critical threshold, at which point multiple feedback loops amplify small disturbances into planetary-scale disruptions. It's the same principle that governs avalanches or stock market crashes. Gradual stress accumulation reaches a tipping point where the slightest additional pressure triggers catastrophic system-wide failure. Atmospheric monitoring stations are beginning to detect the early signatures of such system stress. Methane concentrations in Arctic air samples show seasonal spikes that exceed normal variation patterns by significant margins. These spikes don't correlate with known sources like wetland emissions or industrial releases. Instead, they appear to originate from point sources deep beneath the permafrost, suggesting that hydrate deposits are already beginning to destabilize in response to changing pressure conditions. The implications for flood-induced axial displacement are staggering. Traditional models assume that only the water itself contributes to mass redistribution during major flood events. But if those floods simultaneously trigger methane hydrate explosions, the total energy and mass displacement could be orders of magnitude larger than previously calculated. The combined effect might be sufficient to shift Earth's axis by degrees rather than the arc minutes that conventional analysis suggests. Ocean current monitoring reveals additional mechanisms that could amplify these effects. Deep water circulation patterns, which have remained relatively stable for thousands of years, show signs of significant disruption. Temperature and salinity measurements indicate that thermohaline circulation, the global conveyor belt of deep ocean currents, is beginning to slow in some regions while accelerating in others. These changes create pressure differentials that affect how water masses respond to gravitational forces during flood events. And when oceanographers model the effects of massive freshwater inputs from simultaneous ice sheet collapses, they discover that current circulation patterns don't simply adjust gradually to the new conditions. Instead, they undergo rapid reorganization that can redirect enormous volumes of water across entire ocean basins within decades. These redirected flows create their own momentum effects, adding rotational energy to flood-induced mass displacement. The Pacific Ring of Fire provides a particularly compelling example of how these various factors interact. Seismic monitoring stations around the Pacific Rim are recording increased activity levels that correlate with both tidal stress cycles and atmospheric pressure changes associated with Arctic permafrost instability. The correlation suggests that the Earth's crustal systems are already responding to developing instabilities in ways that could amplify future flood events. Volcanic activity patterns show similar correlations. Eruption frequencies along mid-ocean ridges have increased significantly over the past several decades, while the chemical composition of volcanic gases indicates deeper crustal involvement than typical surface volcanism would produce. These deep eruptions release materials from crustal layers that haven't been disturbed for thousands of years, suggesting that pressure changes are propagating much deeper into the Earth's structure than surface observations alone would indicate. The magnetic field fluctuations detected by satellite monitoring systems provide another piece of the puzzle. Earth's magnetic field is generated by convection currents in the liquid iron core, and these currents are sensitive to changes in the planet's rotational dynamics. The increasing frequency and magnitude of magnetic field variations suggest that core dynamics are already responding to developing surface instabilities. These magnetic changes have practical implications that extend beyond academic interest. Navigation systems that depend on magnetic compass readings are becoming increasingly unreliable in certain regions. Airline pilots report compass variations that require frequent recalibration, while ship navigation systems show errors that grow larger each year. The changes aren't random, but follow patterns that correlate with the locations of ancient flood boundaries preserved in geological records. Animal migration patterns provide additional confirmation that fundamental environmental systems are entering states of instability. Species that have followed the same seasonal routes for thousands of years are suddenly appearing in unexpected locations or failing to appear in traditional habitats. Marine mammals are stranding themselves on beaches far from their normal ranges, while bird populations are shifting their nesting areas by hundreds of miles from historical locations. These behavioral changes suggest that the animals are responding to environmental cues that human instruments are only beginning to detect. Their navigation systems evolved over millions of years to respond to subtle magnetic and gravitational signals, may be more sensitive to developing planetary instabilities than our technological monitoring networks. The consistency of these behavioral changes across multiple species and geographical regions indicates that whatever signals they're responding to operate on a global scale. Indigenous knowledge keepers have begun sharing observations that align disturbing well with these scientific measurements. Elders from Arctic communities describe changes in ice formation patterns that don't match seasonal expectations. Traditional hunting and fishing grounds are yielding different species than have been found there for generations. Weather patterns that once followed predictable seasonal cycles are becoming increasingly erratic and extreme. These observational reports carry particular weight because they represent continuous monitoring by people whose survival has depended on accurate environmental assessment for thousands of years. Their ancestors survived previous catastrophic cycles by maintaining detailed knowledge of natural warning signs. The fact that current observations are triggering traditional emergency protocols suggests that we may be approaching conditions that haven't been seen for thousands of years. Archaeological investigations of ancient settlement patterns reveal how previous civilizations responded to developing instabilities. Sites that show evidence of rapid abandonment around the time of major flood events often contain artifacts and structures that suggest the inhabitants had advance warning of approaching catastrophe. Storage facilities filled with preserved foods, transportation equipment positioned for rapid evacuation, and communication systems designed to coordinate large-scale population movements. These preparations weren't the result of sudden panic, but of systematic planning based on accumulated knowledge of cyclical environmental patterns. The civilizations that survived previous axial displacement events were those that maintained institutional memory of the warning signs and developed contingency plans for planetary-scale disruption. Their success depended not on preventing the catastrophe, but on adapting to its inevitable occurrence. Modern climate science is beginning to recognize similar patterns in contemporary data. Researchers studying ice sheet dynamics have identified acceleration thresholds, beyond which glacial collapse becomes self-sustaining. Ocean current monitoring reveals bifurcation points where circulation patterns can flip rapidly between stable states. Atmospheric modeling shows tipping points where weather systems reorganize into entirely different configurations. The convergence of these various threshold effects suggests that Earth's environmental systems are approaching a state of synchronized instability, similar to conditions that preceded previous axial displacement events. The difference is that we now possess the technological capability to monitor these developments in real time and potentially take preventive action or at least prepare for the consequences. But preparation requires acknowledging possibilities that extend far beyond the gradual climate change scenarios that currently dominate policy discussions. We need to consider what would happen if sea levels rose not by meters over decades, but by tens of meters within years. We need to plan for the possibility that familiar coastlines could disappear entirely, while new land masses emerge from previously submerged areas. We need to develop systems that can function even if the basic geographical assumptions underlying our civilization prove incorrect. The ancient monument builders understood this challenge and created solutions that continue to function thousands of years after their construction. Their stone archives preserve essential knowledge in forms designed to survive any conceivable disruption. Their astronomical alignments maintain accuracy despite multiple axial displacement events. Their construction techniques demonstrate engineering principles that remain sound regardless of changing environmental conditions. We face the same fundamental challenge with greater capabilities, but also greater vulnerabilities. Our global civilization possesses unprecedented technological power, but it depends on infrastructure and systems that assume planetary stability. The question becomes whether we can develop the institutional wisdom to prepare for possibilities that our immediate experience suggests are impossible, but that geological history indicates are inevitable. The data streaming in from monitoring stations around the world suggests that time may be shorter than we imagine. The various instability indicators are beginning to converge in ways that historical patterns suggest precede major threshold events. Whether we interpret these signs as warnings to heed or simply as natural variations to monitor may determine whether our civilization joins the ranks of those that successfully adapted to planetary change or becomes another mysterious gap in the archaeological record. The next phase of investigation must focus on identifying the specific trigger mechanisms that could initiate cascade failures in Earth's environmental systems. Understanding these mechanisms offers our best hope of either preventing catastrophic outcomes or at least preparing for their consequences. The ancient civilizations that survived previous cycles left us more than monuments. They left us a roadmap for navigating planetary-scale uncertainty, encoded in stone and preserved in oral traditions that are only now beginning to make scientific sense. Scientific sense. The research vessel Aurora cuts through Antarctic waters as marine geologist Dr. James Northcott monitors instruments that reveal something extraordinary beneath the ice. Sonar returns show massive cavities where solid ice should exist, chambers large enough to contain entire cities. These aren't natural formations carved by gradual melting. The geometric precision, the smooth walls, the interconnected passages all suggest rapid excavation by forces that defy conventional understanding of glacial dynamics. Temperature sensors lowered into these cavities register readings that challenge everything glaciologists thought they knew about ice sheet stability. The water inside these chambers maintains temperatures several degrees above freezing despite being surrounded by ice that should be well below zero. Chemical analysis reveals mineral concentrations that could only result from contact with deep crustal materials, suggesting these cavities extend far deeper than ice thickness alone could account for. Similar discoveries emerge from drilling operations across the Antarctic continent. Core samples from depths that should contain solid ice instead reveal layers of compressed organic material, flash-frozen vegetation, and marine sediments. The stratigraphy makes no sense according to current models of ice sheet formation. Tropical plant material appears above Arctic algae deposits, while deep ocean sediments sit beneath what should be terrestrial ice formations. Radiocarbon dating of these organic layers produces results that cluster around specific time periods, the same intervals that appear in flood deposit records from every other continent. The pattern suggests that Antarctica experienced rapid environmental transitions that transformed the continent from temperate to Arctic conditions within geological instants. These weren't gradual climate shifts occurring over thousands of years, but sudden reorganizations that preserved entire ecosystems in crystalline suspension. The implications for ice sheet stability are profound. If Antarctic ice formed rapidly through sudden climate shifts rather than gradual accumulation over millennia, then it could disappear with equal rapidity under the right conditions. The enormous weight of accumulated ice, currently assumed to provide gravitational stability, might instead represent a massive potential energy source waiting for the proper trigger to release. Gravitational mapping of the Antarctic continent reveals mass distribution patterns that support this hypothesis. The ice sheet doesn't rest uniformly on bedrock as traditional models suggest. Instead, vast sections appear to be supported by complex networks of chambers and cavities that could destabilize catastrophically if internal pressure conditions changed suddenly. The continent resembles a massive honeycomb structure rather than a solid block of ice and rock. Seismic monitoring stations positioned around Antarctica's perimeter detect low-frequency vibrations that propagate through the ice sheet in regular patterns. These aren't random tremors caused by settling or thermal expansion. They follow rhythmic cycles that correlate with tidal forces and atmospheric pressure changes, suggesting that the entire ice mass responds dynamically to external influences. The vibrations indicate that Antarctica is far from the stable, static system that climate models assume. Deep ice core analysis reveals additional evidence of rapid system transitions. Atmospheric gas concentrations preserved in ice layers show dramatic fluctuations that occurred within decades rather than centuries. Oxygen isotope ratios indicate temperature swings of enormous magnitude, changes that would have required complete reorganization of global atmospheric circulation patterns. These fluctuations align temporally with the flood deposit boundaries found in sediment records worldwide. The most disturbing discovery involves the behavior of subglacial lakes, bodies of liquid water that exist beneath miles of Antarctic ice. These lakes, once thought to be isolated and stable, show evidence of sudden drainage and refilling cycles. Satellite monitoring reveals that entire lake systems containing billions of gallons of water can empty completely within months, then refill just as rapidly from unknown sources. When hydrologists model the drainage patterns of these subglacial lakes, they discover connection networks that extend across the entire continent. Water released from lakes in East Antarctica appears in West Antarctic drainage systems within years, suggesting underground flow channels that operate on continental scales. The total volume of water in constant circulation beneath the ice sheet approaches the volume of the Great Lakes combined. The implications for flood-induced axial displacement become clear when the physics of this hidden water system are fully considered. If external forces triggered simultaneous drainage of multiple subglacial lake networks, the resulting surface water flows would dwarf any flood in recorded history. But more significantly, the sudden removal of water mass from beneath the ice sheet would destabilize the gravitational balance that keeps the ice in place. Computer simulations of subglacial lake drainage reveal cascade failure mechanisms that could trigger total ice sheet collapse within decades. The initial drainage creates cavities that allow overlying ice to settle and crack. These cracks propagate upward through the ice sheet, creating pathways for surface meltwater to reach the bedrock. The additional water lubricates the interface between ice and rock, allowing massive ice sections to slide toward the ocean at accelerated rates. Ocean temperature monitoring around Antarctica shows warming patterns that could trigger such cascade failures. Deep water currents that have remained stable for thousands of years are beginning to shift their flow patterns, bringing warmer water masses into contact with ice sheet margins that previously experienced only frigid conditions. These temperature changes aren't gradual warming trends, but sudden circulation reorganizations that affect entire ocean basins. Marine biologists studying Antarctic waters report species migrations that suggest major environmental transitions are already underway. Fish populations that have remained in specific temperature zones for their entire evolutionary history are suddenly appearing in waters that should be too warm or too cold for their survival. Krill distributions, the foundation of the Antarctic food chain, show population shifts that indicate fundamental changes in ocean chemistry and circulation patterns. The behavior of Antarctic ice shelves provides additional evidence of accelerating instability. These floating ice platforms, some the size of entire U.S. states, have remained relatively stable for thousands of years. But satellite imagery reveals that several major shelves have begun developing fracture patterns that could lead to catastrophic collapse within decades. The cracks don't follow random stress patterns, but form geometric networks that suggest systematic weakening of the ice structure. When glaciologists analyze the fracture propagation rates in these ice shelves, they discover acceleration patterns that mirror those observed in avalanche and landslide systems just before catastrophic failure. The cracks spread slowly at first, then exponentially faster as they approach critical instability thresholds. Mathematical models of these fracture networks predict that several major ice shelves could collapse simultaneously within the next several decades. The collapse of Antarctic ice shelves wouldn't just contribute to sea level rise through direct ice loss. These shelves currently act as buttresses that hold back the massive ice sheets on the continental interior. Their removal would allow interior ice to flow toward the ocean at unprecedented rates, potentially raising global sea levels by tens of meters within centuries rather than millennia. But the most significant consequence involves the redistribution of mass that would accompany such rapid ice loss. Antarctica contains approximately 90% of the world's fresh water in frozen form. The sudden release of even a fraction of this mass would create gravitational anomalies sufficient to affect Earth's rotational dynamics. The planet's axis of rotation, currently stabilized by the polar ice masses, could shift significantly if Antarctic ice redistributed rapidly to lower latitudes. Paleoclimate records from previous interglacial periods reveal evidence that such rapid ice redistributions have occurred repeatedly throughout Earth's history. Marine sediment cores show layers of Antarctic-derived materials deposited in tropical oceans, indicating that polar ice has reached equatorial latitudes multiple times during past climate transitions. The timing of these deposits correlates with evidence of major flood events and associated axial displacement episodes. Modern satellite monitoring of Earth's rotational dynamics shows fluctuations that suggest the planet's axis is already responding to changing ice mass distributions. Precise measurements of day length reveal variations that correlate with seasonal ice accumulation and melting cycles, but with amplitudes that exceed what current ice volume should produce. The discrepancy suggests that ice mass changes are having disproportionate effects on planetary rotation, possibly due to resonance amplification mechanisms. The International Earth Rotation Service, responsible for maintaining precise time standards, reports increasing difficulty in predicting rotational variations. Leap seconds, the adjustments needed to keep atomic clocks synchronized with Earth's rotation, are becoming more frequent and less predictable. The pattern suggests that planetary rotation is entering a state of increased variability that could precede more dramatic changes. Astronomical observations provide additional confirmation that Earth's rotational stability is decreasing. Precise measurements of star positions reveal systematic drifts that indicate the planet's orientation in space is changing more rapidly than historical norms would suggest. These changes affect GPS satellite accuracy, require constant recalibration of telescope pointing systems, and create navigation errors that grow larger each year. The convergence of these various indicators suggests that Earth's environmental systems are approaching a state of synchronized instability. Antarctic ice sheets showing signs of imminent collapse, subglacial water systems entering drainage cycles, ocean circulation patterns reorganizing, and planetary rotation displaying increasing variability. Each system alone might represent natural variation, but their simultaneous destabilization suggests approaching threshold conditions. Historical analysis of previous threshold events reveals that they don't occur gradually over centuries, but rapidly over decades once critical instability levels are reached. The transition from stable to chaotic behavior happens suddenly, triggered by relatively minor disturbances that cascade through interconnected systems. The geological record preserves evidence of such transitions occurring within human lifespans, leaving survivors to rebuild civilization in dramatically altered environments. Indigenous knowledge systems from around the world preserve detailed accounts of how previous civilizations recognized and prepared for such transitions. The stories speak of ice mountains that walked into the sea, of waters that came from the sky in quantities that drowned entire continents, of the Earth itself shaking so violently that familiar stars disappeared from view. These aren't mythological accounts, but observational records preserved across thousands of years of surviving cyclical catastrophes. Modern climate science is beginning to recognize patterns in contemporary data that match these traditional warning systems. Ice sheet acceleration rates are approaching thresholds that indigenous accounts associate with imminent collapse. Ocean temperature fluctuations are displaying characteristics that traditional knowledge links to major flood events. Atmospheric circulation patterns are showing instabilities that historical accounts connect to axial displacement episodes. The question becomes whether modern civilization can develop the institutional wisdom to interpret these warning signs and prepare for their consequences. Our technological capabilities far exceed those of previous civilizations, but our social and economic systems have evolved to assume environmental stability. The infrastructure supporting global civilization depends on predictable climate zones, stable coastlines, and consistent seasonal patterns. Archaeological evidence suggests that civilizations which successfully navigated previous threshold events were those that maintained distributed knowledge systems and developed adaptive technologies. They created redundant communication networks, established communities in geologically stable regions, and preserved essential information in forms designed to survive any conceivable disruption. Their success came not from preventing catastrophic change, but from preparing to function during and after major environmental transitions. The challenge facing contemporary society involves scaling these ancient adaptive strategies to global industrial civilization. We need to develop systems that can maintain functionality even if fundamental geographical assumptions prove incorrect. This means creating information networks that don't depend on satellite systems that could be disrupted by axial displacement, establishing food production capabilities that can operate under radically different climate conditions, and preserving technological knowledge in forms that could survive infrastructure collapse. More fundamentally, we need to expand our conception of natural disaster preparedness to include events that could literally reshape the planet's geography. The ancient civilizations that built monuments aligned to vanished star patterns understood that environmental stability is temporary. Their stone archives continue to function thousands of years after construction, testament to engineering principles that remain valid regardless of changing planetary conditions. The data streaming in from monitoring stations around the world suggests that we may be approaching another such transition period. The various instability indicators are beginning to converge in ways that historical patterns associate with major threshold events. Whether we interpret these convergences as natural variations to monitor or as warnings requiring immediate preparation may determine whether our civilization adapts successfully to planetary change or becomes another unexplained gap in the archaeological record. The research vessel Aurora continues its Antarctic survey, each data point adding to a growing picture of planetary systems entering states of critical instability. Dr. Northcott adjusts his instruments one final time as the ship heads toward deeper waters, carrying measurements that may prove crucial for understanding humanity's next great challenge. The ice behind them gleams in the polar sun, beautiful and serene, hiding beneath its surface the mechanisms that could reshape the world within our lifetimes. The ancient monument builders left us more than stone structures. They left us a blueprint for surviving planetary-scale uncertainty, encoded in architectural precision and preserved in oral traditions that modern science is only beginning to decode. Their message across time is clear. The Earth is not the stable foundation we imagine, but a dynamic system capable of sudden transformation. Our survival depends not on preventing such changes, but on preparing to adapt when they inevitably occur. The morning sun reflects off Antarctic ice as research teams prepare for another day of measurements, unknowing that each reading brings us closer to understanding forces that could soon turn our familiar world into something unrecognizable. The question is no longer whether such changes will occur, but whether we will recognize the warnings in time to prepare for a future where the only constant is the certainty of change itself. The only constant is the certainty of change itself. The research station in northern Siberia operates in perpetual twilight, its instruments recording phenomena that challenge fundamental assumptions about planetary stability. Dr. Katya Volkov adjusts the deep core drilling equipment as her team extracts samples from permafrost layers that reveal impossible chronologies. Mammoth tusks emerge from depths that should contain only ancient marine sediments. Tropical wood fragments appear in layers that carbon dating places at the height of supposed ice ages. Each core sample tells the same story. The environmental history preserved in frozen Earth doesn't match the gradual climate transitions that conventional models predict. The permafrost cores reveal compression patterns that suggest rapid burial rather than slow accumulation. Organic materials show evidence of flash freezing that preserves cellular structures in pristine condition, as if entire ecosystems had been instantly transformed from temperate to Arctic conditions. Chemical analysis of the frozen soil reveals mineral compositions that could only result from massive water transport, indicating that these materials originated thousands of miles from their current locations. Similar anomalies emerge from drilling operations across the Arctic Circle. Teams working in Alaska, northern Canada, and Greenland report identical findings. Tropical plant pollens in Arctic sediments, marine fossils at inland elevations, freshwater algae preserved beneath layers of sea salt. The evidence points to environmental transitions so rapid and comprehensive that entire biomes were transported and deposited in single catastrophic events. Ground-penetrating radar surveys of these permafrost regions reveal structural features that defy explanation through conventional geological processes. Massive underground chambers stretch for miles beneath the frozen surface, their walls showing evidence of rapid excavation by flowing water under enormous pressure. These aren't natural cave systems formed over millions of years, but erosion channels carved in geological instants by floods that moved with the force of tsunamis. The discovery of these subterranean networks has profound implications for understanding how water behaves during planetary-scale flood events. Traditional hydraulic models assume that floodwater flows along surface topography, carving channels and depositing sediments according to gravitational gradients. But the Arctic evidence suggests that during extreme events, water can burrow deep into the Earth's crust, creating pressure waves that propagate through solid rock and destabilize underground formations. Seismic monitoring stations positioned above these buried channel networks detect ongoing subsidence as the permafrost continues to shift and settle. The movements aren't random thermal expansion effects, but coordinated adjustments that suggest the underground structure remains dynamically active. Temperature sensors reveal that some of these buried chambers maintain above freezing conditions despite being surrounded by permafrost that hasn't thawed for thousands of years. The source of this underground heat appears to be geothermal activity, triggered by the massive pressure changes that occurred during the original flood events. When enormous volumes of water suddenly load and unload the Earth's surface, the resulting stress waves can activate dormant geological systems deep beneath the surface. Magma chambers that remain stable for millennia can destabilize, creating new sources of geothermal energy that persist long after the surface events that triggered them. This mechanism explains why permafrost regions are experiencing accelerated thawing despite surface temperature changes that should produce only gradual effects. The underground heating isn't driven by atmospheric warming, but by geological processes that were initiated thousands of years ago and continue to evolve beneath the frozen surface. As these geothermal systems become more active, they create positive feedback loops that accelerate surface thawing and increase the likelihood of catastrophic permafrost collapse. The implications for methane hydrate stability are particularly concerning. These crystalline structures depend on specific combinations of pressure and temperature to remain stable. Underground heating from activated geothermal systems can destabilize hydrate deposits across vast areas simultaneously, creating the potential for explosive gas releases that could dwarf any previous natural disaster. The energy stored in Arctic methane hydrates exceeds that of all known fossil fuel reserves combined. Recent atmospheric monitoring reveals methane concentration spikes that suggest some hydrate deposits are already beginning to destabilize. The spikes don't correlate with known sources or seasonal patterns, but appear randomly across the Arctic region with intensities that indicate massive underground releases. Chemical analysis of these methane emissions reveals isotopic signatures consistent with hydrate decomposition rather than biological or industrial sources. The timing of these methane releases correlates with increased seismic activity along fault systems that weren't previously considered geologically active. Earthquake swarms in regions that have remained stable for thousands of years suggest that underground pressure changes are propagating through crustal systems in ways that connect distant geological features. The Earth's crust appears to be responding as an integrated system rather than a collection of isolated local phenomena. Ocean current monitoring reveals similar systematic changes in marine circulation patterns. Deep water masses that have maintained consistent temperature and salinity characteristics for centuries are beginning to show significant variations. These changes don't follow predictable patterns based on surface weather conditions or seasonal cycles, but appear to result from systematic reorganization of global circulation systems. The reorganization affects how ocean waters transport heat, nutrients, and dissolved gases around the planet. Current systems that have remained stable since the end of the last ice age are showing signs of fundamental instability. Computer models of ocean circulation suggest that these systems exist in multiple stable states and can flip rapidly between configurations when disturbed beyond critical thresholds. Marine biologists studying deep ocean ecosystems report population changes that indicate major environmental transitions are already underway. Species that have occupied specific depth and temperature ranges for their entire evolutionary history are suddenly migrating to regions that should be unsuitable for their survival. These movements aren't gradual range expansions, but rapid relocations that suggest the animals are responding to environmental cues that human instruments are only beginning to detect. The most significant migrations involve deep sea species that serve as indicators of ocean current stability. These organisms depend on specific combinations of temperature, pressure, and chemical conditions that exist only in particular water masses. Their sudden appearance in unexpected locations suggests that deep ocean currents are transporting water masses to regions where they haven't been present for thousands of years. Paleoceanographic studies of marine sediment cores reveal that similar circulation reorganizations have occurred repeatedly throughout Earth's history. The timing of these events correlates precisely with evidence of major flood episodes and associated axial displacement events. The pattern suggests that massive surface water movements trigger cascade effects that propagate through the entire global ocean system. The cascade mechanisms involve complex interactions between surface flooding, deep water formation, and planetary rotation dynamics. When enormous volumes of fresh water suddenly enter the ocean system during continental flood events, they don't simply mix with existing water masses. Instead, they create density gradients that can shut down established circulation patterns and initiate entirely new flow configurations. These circulation changes affect global heat transport in ways that can trigger rapid climate transitions. Ocean currents that normally carry warm water to polar regions can reverse or disappear entirely, causing regional temperatures to change by tens of degrees within decades. Conversely, currents that normally transport cold polar water to temperate regions can intensify, bringing Arctic conditions to previously moderate climates. The atmospheric response to such ocean circulation changes involves reorganization of weather patterns on continental scales. Storm tracks that have followed consistent paths for centuries can shift by thousands of miles, bringing unprecedented weather conditions to regions that lack the infrastructure to cope with such changes. Seasonal patterns that have remained predictable for human memory can disappear entirely, replaced by chaotic weather systems that defy traditional forecasting methods. Archaeological evidence suggests that previous civilizations experienced exactly these types of rapid environmental transitions. Settlement patterns show coordinated abandonment of entire regions, followed by equally rapid colonization of areas that had previously been uninhabitable. The relocations weren't gradual migrations driven by population pressure or resource depletion, but sudden movements that suggest environmental conditions change faster than human adaptation could accommodate. The preserved artifacts from these abandoned settlements often show evidence of hasty departure. Tools left in mid-use, food stores abandoned before consumption, construction projects halted before completion. These aren't signs of gradual cultural decline, but of populations forced to abandon familiar territories with little advance warning. The archaeological signature is consistent with communities that faced environmental changes too rapid for normal adaptation strategies. Modern climate monitoring reveals that we may be approaching similar conditions. The various environmental indicators are beginning to display the same patterns of accelerating instability that preceded previous transition events. Ocean circulation changes, atmospheric reorganization, geological system activation, and ecosystem disruption are occurring simultaneously across multiple planetary systems. The convergence of these indicators suggests that Earth's environmental systems are approaching critical thresholds, beyond which small additional disturbances could trigger catastrophic reorganization. The mathematical models that govern such systems reveal that stability decreases exponentially as threshold conditions approach, meaning that relatively minor events could precipitate changes of enormous magnitude. Historical analysis of previous threshold events reveals that they typically unfold over periods of decades rather than centuries, once critical conditions are reached. The transition from stable to chaotic behavior happens suddenly, leaving little time for societies to adapt their infrastructure and institutions to radically different environmental conditions. The civilizations that survive such transitions were those that maintained the flexibility to relocate rapidly and the knowledge systems to function under completely altered circumstances. Contemporary civilization faces the same challenge with both greater capabilities and greater vulnerabilities than previous societies. Our global communication networks and transportation systems provide unprecedented ability to coordinate large-scale responses to environmental changes. But our technological infrastructure depends on stable energy supplies, predictable weather patterns, and consistent geographical relationships that could be disrupted by rapid environmental transitions. The ancient civilizations that built monuments designed to function across multiple environmental transition cycles understood that survival depends not on preventing change, but on maintaining functionality during and after major planetary reorganizations. Their stone archives continue to preserve essential information thousands of years after construction, testament to engineering principles that remain valid regardless of changing environmental conditions. The challenge facing modern society involves scaling these ancient adaptive strategies to contemporary global civilization. We need to develop systems that can maintain essential functions even if fundamental environmental assumptions prove incorrect. This means creating distributed networks that don't depend on centralized infrastructure, establishing communities in geologically stable regions, and preserving critical knowledge in forms that could survive major disruptions. The data streaming in from monitoring stations around the world suggests that time for such preparations may be shorter than conventional climate projections indicate. The various instability indicators are converging in patterns that historical analysis associates with imminent threshold events. Whether we recognize these convergences as warnings requiring immediate action or dismiss them as natural variations to monitor may determine whether our civilization successfully navigates the next planetary transition or becomes another archaeological mystery for future societies to contemplate. The research continues in laboratories and field stations across the globe, each measurement adding to an increasingly clear picture of planetary systems entering states of critical instability. The scientists working in these remote locations understand that they are documenting more than climate change. They are recording the early stages of processes that could reshape the world within their lifetimes, processes that have occurred repeatedly throughout Earth's history, but which modern civilization has never experienced. The ancient monument builders left us messages encoded in stone, mathematical relationships that remain constant regardless of changing planetary conditions. Their precision across multiple axial displacement events demonstrates engineering principles that transcend any single environmental configuration. Perhaps most importantly, they demonstrated that human knowledge and achievement can survive even the most dramatic planetary transformations if properly preserved and transmitted across the cycles of destruction and renewal that characterize Earth's long history. The question facing contemporary humanity is whether we will develop the wisdom to interpret the warnings that our instruments are detecting and prepare for possibilities that extend far beyond the gradual changes that dominate current policy discussions. The geological record makes clear that Earth's environmental systems are capable of reorganization so rapid and comprehensive that they literally turn the world upside down within human lifetimes. Our survival may depend on acknowledging these possibilities and developing the adaptive capabilities that allowed previous civilizations to navigate similar transitions successfully. The ancient navigators who crossed vast oceans without compasses understood something we've forgotten. They read the water itself, watching how waves bent around invisible obstacles, feeling the subtle changes in current temperature that revealed distant land masses. Their knowledge wasn't written in charts, but encoded in generations of careful observation. Now, modern oceanographers studying wave propagation patterns are rediscovering principles these seafarers knew by instinct. The ocean doesn't simply flow from high places to low places, it remembers. Dr. Hassan al-Rashid guides his research vessel through waters that behave unlike anything in maritime textbooks. The GPS readings shift constantly, not from equipment failure, but from gravitational anomalies that pull navigation satellites off their predicted orbits. Deep beneath the surface, mass concentrations that shouldn't exist according to seafloor maps create localized distortions in space-time itself. The water moves in spirals and countercurrents that follow patterns invisible to surface observation, but perfectly logical once you understand what's happening far below. These gravitational signatures tell stories of redistribution events so massive they left permanent scars in Earth's structure. When continental flood systems collapse, they don't simply drain into existing ocean basins. They carve new pathways through the planet's crust, creating underground river systems that continue flowing long after surface conditions have stabilized. These buried waterways transport sediments and dissolve minerals across thousands of miles, creating the chemical anomalies that puzzle marine geologists. The process operates like a planetary circulatory system. Surface floods create pressure that forces water deep into crustal fractures. This pressurized flow excavates underground channels that connect distant geological formations. Over time, these channels develop their own flow patterns independent of surface topography. The result is a hidden network of aquifers and underground streams that can suddenly emerge at the surface when geological stresses create new outlet points. Satellite imagery reveals circular formations in ocean floors that mark the locations where these underground systems have breached the surface in the past. The formations appear as perfect rings of disturbed sediment, some hundreds of kilometers in diameter, surrounding central depressions that extend far deeper than normal seafloor features. Chemical analysis of these formations reveals mineral compositions that could only result from deep crustal materials being transported to the surface by high-pressure water flow. The energy required for such transport defies conventional understanding of hydrological systems. Water flowing under normal gravitational conditions lacks the force needed to excavate channels through solid rock or transport massive boulders across continental distances. But when surface loading from catastrophic floods creates pressure waves that propagate through the Earth's crust, the resulting forces can accelerate underground water to velocities that approach those of industrial cutting systems. Recent discoveries in deep ocean trenches reveal evidence of these high-velocity water systems in action. Sediment cores from abyssal depths contain layers of materials that originated thousands of miles away and at much higher elevations. The transport mechanism couldn't have been normal surface erosion and deposition. Instead, the materials show signs of having been carried by pressurized flows that maintained coherent streams across entire ocean basins. The implications for understanding flood-induced mass redistribution are profound. Traditional models assume that floodwater redistributes mass only through surface processes like erosion, deposition, and direct displacement. But if floods also trigger underground transport systems that move materials through the planet's interior, then the total mass redistribution during major events could be orders of magnitude larger than surface observations would suggest. Underground mass transport could explain why some regions show evidence of sudden elevation changes that can't be accounted for by known geological processes. Mountain ranges that appear to have risen hundreds of meters within centuries rather than millennia. Valley systems that seem to have been carved overnight by forces far exceeding any known flood events. Coastal formations that suggest sea levels change by enormous amounts within human memory rather than geological time. The mechanism involves feedback loops between surface loading and deep crustal response. When massive floods redistribute water across continents, the resulting pressure changes propagate through the Earth's interior as elastic waves. These waves can destabilize underground formations that have remained stable for thousands of years, triggering secondary mass movements that amplify the surface effects. Deep crustal monitoring stations detect these pressure waves as they travel through the planet's interior. The waves don't dissipate uniformly with distance as simple elastic theory would predict. Instead, They follow patterns that suggest the Earth's interior contains structural features that focus and amplify the energy. Underground chambers, fault systems, and mineral boundaries act as waveguides that concentrate flood-generated pressure in specific locations. When these concentrated pressure waves reach critical amplitude, they can trigger sudden failures in underground formations. Rock layers that have supported overlying structures for millennia can collapse in geological instants, creating new underground cavities that alter surface topography. The process can cause entire regions to subside or uplift without any surface indication of the underground changes responsible for the movement. Archaeological sites provide evidence that such underground-driven surface changes have occurred repeatedly throughout human history. Ancient cities built on apparently stable ground show signs of sudden structural failure that can't be explained by earthquakes, volcanism, or normal foundation settling. The damage patterns suggest that the ground itself changed elevation or orientation rapidly enough to destroy buildings designed for different loading conditions. Some of these archaeological sites contain artifacts that seem to preserve memories of such events. Stone carvings depicting the earth opening and swallowing structures, religious texts describing underground waters that rise to reshape the surface world, oral traditions that speak of the ground breathing, rising and falling like a living thing, responding to forces beyond human understanding. Modern geophysical surveys of these sites reveal underground features that support these traditional accounts. Complex networks of cavities and channels exist beneath locations where ancient texts describe earth movements. Ground-penetrating radar shows structural features that could destabilize if underground water pressures change suddenly. The evidence suggests that ancient peoples understood geological processes that modern science is only beginning to recognize. The pattern extends beyond individual archaeological sites to entire regions. River systems that ancient accounts describe as flowing in opposite directions than they do today. Lake systems that historical records indicate appeared and disappeared within single generations. Coastlines that traditional knowledge places hundreds of miles from their current locations. Each apparent discrepancy between ancient accounts and modern geography becomes logical when viewed through the lens of underground mass redistribution. The mathematical analysis of these redistribution events reveals why they produce such dramatic effects on planetary rotation. Earth's moment of inertia depends not only on how mass is distributed across the surface, but also on how it's arranged within the planet's interior. Underground mass movements can shift the planet's center of mass by distances sufficient to alter rotational dynamics, even when surface changes appear relatively minor. Computer simulations of coupled surface-subsurface mass redistribution reveal threshold effects that traditional models miss entirely. Below certain levels of underground activity, surface floods produce only local effects that dissipate over time. Above critical thresholds, underground systems activate that can transport mass across continental distances and trigger surface changes far from the original flood locations. The activation of these underground systems appears to follow patterns that correlate with astronomical cycles. Gravitational stresses from solar and lunar influences affect not only surface tides, but also the behavior of underground water systems. When these astronomical forces align with flood-generated pressure waves, the combined effects can exceed the thresholds needed to trigger large-scale underground mass transport. Monitoring stations positioned above known underground channel systems detect increasing activity levels that suggest these systems are responding to developing surface instabilities. Water flow rates in deep aquifers are accelerating beyond historical norms. Pressure variations in underground chambers are displaying amplitudes that approach critical thresholds. Chemical compositions of deep groundwater are changing in ways that indicate increased interaction between surface and subsurface systems. The convergence of these indicators with surface instability signals suggests that Earth's hydrological systems are entering a state of integrated activation. Surface and subsurface water systems that normally operate independently are beginning to interact in ways that could amplify small disturbances into planetary-scale redistributions. The result could be mass movements sufficient to alter Earth's rotational axis by degrees, rather than the tiny wobbles that characterize normal planetary motion. Historical analysis reveals that previous axial displacement events coincided with evidence of massive underground water system activation. Geological formations that preserve records of these events show characteristic signatures of high-pressure underground flow. Mineral deposits that could only form under extreme pressure conditions. Erosion patterns that require water velocities far exceeding surface flow capabilities. Chemical alterations that indicate deep crustal materials were transported to surface locations. The ancient civilizations that survived these events appear to have developed technologies for monitoring underground water system activity. Their monuments often sit above locations where modern surveys reveal complex subsurface channel networks. The positioning suggests they understood the relationship between underground water flow and surface stability, choosing construction sites that would remain stable even during major hydrological reorganizations. Some of these ancient monitoring systems may still be functional. Stone structures that exhibit acoustic properties designed to amplify underground sounds. Chamber configurations that could detect pressure changes in subsurface water systems. Architectural features that align with underground channel orientations in ways that would make structural changes visible through surface observations. The precision of these ancient installations suggests sophisticated understanding of underground hydrological processes. Their builders didn't simply observe surface water behavior, but developed methods for tracking the movement of water through the planet's interior. This knowledge allowed them to predict when underground systems might activate and trigger the surface changes that could destabilize civilizations dependent on geographical stability. Modern attempts to replicate this monitoring capability using contemporary instruments are revealing the complexity of the underground systems these ancient engineers understood. Networks of interconnected chambers and channels that extend far deeper and cover much larger areas than surface topography would suggest. Flow patterns that respond to astronomical influences in ways that indicate the entire system operates as a unified planetary mechanism rather than a collection of local phenomena. The realization that Earth's water systems operate on multiple levels simultaneously transforms our understanding of how flood events could trigger axial displacement. The planet doesn't simply respond to surface mass redistribution, but to integrated changes that involve both surface and subsurface components. When these systems activate simultaneously, their combined effects can exceed the thresholds needed to alter planetary rotation dynamics. The question facing contemporary civilization is whether we can develop the monitoring capabilities and institutional wisdom needed to track these multi-level processes and prepare for their consequences. The ancient civilizations that built stone archives designed to function across multiple planetary transition cycles understood that survival depends on maintaining awareness of forces that operate on timescales longer than individual human lifetimes. Their monuments continue to function thousands of years after construction, demonstrating engineering principles that remain valid regardless of changing planetary conditions. Perhaps more importantly, they prove that human knowledge and achievement can survive even the most dramatic environmental transitions if properly preserved and transmitted across the cycles of stability and disruption that characterize Earth's long history. The underground networks that honeycomb our planet operate according to principles that challenge every assumption about hydrological stability. Dr. Chen Wei descends into a limestone cavern system beneath the Appalachian Mountains, her instruments detecting water flow patterns that defy conventional physics. The streams here don't follow gravitational gradients as surface rivers do. Instead, they spiral upward through vertical shafts, maintaining pressures that should be impossible at these depths. Chemical analysis reveals that this water originated in aquifers hundreds of miles away, transported through underground channels that modern geology insists cannot exist. The cavern walls bear scars that tell stories of forces beyond normal underground erosion. Perfectly circular holes drilled through solid rock, their surfaces polished to mirror smoothness. Spiral grooves that wind through limestone formations like the threads of enormous screws. These aren't natural formations carved by patient water flow over millennia. They show evidence of rapid excavation by pressurized systems operating under extreme conditions. Similar discoveries emerge from cave systems across multiple continents. Teams exploring underground networks in the Himalayas, the Andes, and the African Rift Valley report identical features. High-pressure erosion patterns that could only result from water moving at industrial velocities. Transport signatures indicating that materials have been carried vast distances through underground channels. Pressure release formations that suggest catastrophic drainage events occurred within geological instants. The implications transform our understanding of how planetary water systems respond to major surface disturbances. When continental flood events redistribute massive water volumes across surface topography, they don't simply drain into existing river networks and ocean basins. They create pressure waves that propagate deep into the Earth's crust, activating underground transport systems that can move water and dissolve materials across entire continents. These underground systems operate like a secondary circulatory network, independent of surface drainage patterns but capable of sudden interaction when pressure conditions exceed critical thresholds. During normal periods, surface and subsurface water systems remain largely isolated. But during major flood events, the pressure differentials can breach the barriers between these systems, creating temporary connections that redistribute mass on scales sufficient to affect planetary dynamics. Geophysical surveys reveal that these underground networks extend far deeper and cover much larger areas than surface observations would suggest. Three-dimensional mapping of subsurface channels shows interconnected systems that span entire continents, with main arteries comparable in scale to major surface river systems. The total volume of water in constant circulation through these underground networks approaches that of all surface freshwater combined. The discovery of such extensive underground water systems explains anomalies that have puzzled hydrologists for decades. Springs that suddenly appear in locations where no water source should exist. Rivers that change their flow characteristics without corresponding changes in surface precipitation patterns. Groundwater levels that fluctuate in response to events occurring thousands of miles away. Deep monitoring wells positioned above these underground channel systems detect flow variations that correlate with seismic activity in distant regions. Water levels rise and fall in response to earthquakes occurring on different continents, suggesting that pressure waves propagate through underground water networks faster than they travel through solid rock. The entire system appears to operate as an integrated, pressure-sensitive network that responds to disturbances anywhere within its extent. The mathematical modeling of such integrated systems reveals behaviors that conventional hydrology never anticipated. Small pressure changes in one region can cascade through the entire network, producing amplified responses at locations thousands of miles from the original disturbance. These amplification effects can transform minor surface events into major underground redistributions that affect surface stability across vast areas. Recent satellite gravity measurements detect mass movements that correlate with underground water system activity. Gravitational field variations indicate that significant mass redistributions are occurring within the Earth's interior, independent of visible surface changes. The patterns suggest that underground water systems are transporting materials on scales that affect the planet's moment of inertia distribution. When physicists analyze these gravity variations in the context of planetary rotation dynamics, they discover that underground mass transport could contribute significantly to axial displacement effects. The Earth's rotational axis responds not only to surface mass redistributions, but also to changes in how mass is arranged within the planet's interior. Underground systems that transport water and dissolve materials across continental distances can shift the planetary center of mass by amounts sufficient to alter rotational stability. The timing of underground system activation appears to follow patterns that correlate with astronomical cycles affecting Earth's gravitational environment. Solar and lunar influences that create surface tides also affect the behavior of underground water systems. When these astronomical forces align with flood-generated pressure waves, the combined effects can exceed the thresholds needed to activate large-scale underground mass transport. Historical analysis reveals that major underground system activations have coincided with periods of rapid surface environmental change. Geological formations preserve evidence of massive underground water flow events that occurred during the same time periods when surface flood deposits were laid down across multiple continents. The synchronization suggests that surface and subsurface water systems can enter states of coordinated activation during planetary-scale hydrological events. Archaeological evidence supports this interpretation through discoveries that seem impossible under conventional geological models. Ancient settlements built in locations that should have remained stable for millennia show signs of sudden abandonment due to ground instability. The damage patterns indicate that underground changes cause surface elevations to shift rapidly enough to destroy infrastructure designed for different loading conditions. Some of these archaeological sites preserve artifacts that appear to document underground water system behavior. Stone carvings that depict water emerging from the ground in quantities that dwarf surface springs. Religious texts that describe underground rivers capable of transporting entire landscapes. Oral traditions that speak of the earth drinking vast quantities of surface water during flood events, then releasing it in distant locations through mechanisms beyond normal understanding. Modern attempts to verify these traditional accounts using contemporary monitoring equipment are revealing the sophistication of ancient hydrological knowledge. Ground-penetrating radar surveys of sites mentioned in historical texts often reveal complex underground channel systems exactly where traditional accounts indicate they should exist. The positioning and characteristics of these systems match descriptions preserved in oral traditions, with accuracy that suggests direct observational knowledge. The ancient engineers who built monuments above these underground water systems appear to have understood principles that modern hydrology is only beginning to recognize. Their construction techniques demonstrate awareness that underground water flow could affect surface stability in ways that normal geological processes cannot. Foundation systems designed to remain stable even if underground pressure conditions change dramatically. Drainage systems that could channel underground flow away from critical structures. Architectural features that would remain functional even if local groundwater levels fluctuated by enormous amounts. The precision of these ancient installations suggests systematic monitoring of underground water system behavior over extended time periods. Observatory structures positioned to detect pressure changes in subsurface channels. Acoustic systems designed to amplify sounds generated by underground water flow. Measurement devices that could track variations in underground pressure that might indicate developing instabilities. Contemporary attempts to replicate such monitoring capabilities reveal the complexity of the underground systems these ancient observers tracked. Networks of interconnected chambers and channels that respond to surface loading in ways that affect regional stability. Flow patterns that can reorganize rapidly when external pressures exceed critical thresholds. Pressure wave propagation that can trigger surface changes far from the original disturbance locations. The realization that underground water systems operate as integrated planetary mechanisms transforms our understanding of how flood events could trigger axial displacement. Surface mass redistribution represents only one component of the total system response. Underground mass transport can amplify surface effects by factors that make minor flood events capable of producing major planetary consequences. Climate monitoring stations positioned above known underground channel systems are detecting activity levels that suggest these systems are responding to developing surface instabilities. Flow rates in deep aquifer systems are accelerating beyond historical norms. Pressure variations in underground chambers are displaying characteristics that historical patterns associate with major system activation events. Chemical compositions of deep groundwater are changing in ways that indicate increasing interaction between surface and subsurface water systems. The convergence of these underground system indicators with surface instability signals suggests that Earth's hydrological systems are entering a state of integrated response. Surface and subsurface components that normally operate independently are beginning to interact in ways that could transform minor disturbances into planetary-scale reorganizations. The mathematical models governing such systems reveal that small additional inputs could trigger cascade effects sufficient to alter Earth's rotational dynamics by degrees rather than the minute wobbles that characterize normal planetary motion. The data streams converge like tributaries feeding an ancient river, each measurement adding weight to a conclusion that reshapes everything we thought we knew about our planet's stability. From Arctic permafrost releasing methane signatures of deep instability to Antarctic ice sheets revealing honeycomb structures that could collapse within decades, from underground water networks transporting continental masses through Earth's hidden circulatory system to gravitational anomalies that pull satellites from their predicted orbits, the evidence speaks with unified voice. We stand at the threshold of forces that have reshaped our world repeatedly throughout history. Forces that could turn our familiar geography upside down within our lifetimes. The ancient monument builders encoded their warnings in stone for good reason. They understood what we are only now rediscovering through satellites and seismic arrays. Earth is not the stable foundation we imagine, but a dynamic system capable of sudden transformation. The geological clock continues its patient countdown. Ice accumulates in patterns that history suggests will trigger massive instability. And the question that remains is whether we will heed the warnings written in stone and carved into the planet's memory, or whether future archaeologists will puzzle over our civilization's sudden disappearance, just as we wonder about the mysterious gaps that mark previous moments when the world turned upside down. The choice, for now, remains ours.